No, I'm not sure why. Ah, okay, so Kaltura just started. So sorry for the slight delay. Okay, so today we continue with the study of Jacobi fields. Okay, and this is lecture 6. So I would like to spend much more time, than they do in the book about Jacobi fields. So I will try to present quite in a lot of details. First, the notion of variation of curve, which is quite important to understand the notion of Jacobi fields. So if we have a curve from the manifold, from the interval 0, 1 into the manifold, so 1, as I told you, is arbitrary. That is, I could work, if I wanted on any finite time interval. So if I consider a smooth curve from 0, 1 to m, what we call a variation of m, variation of gamma. So you should imagine something like this, gamma 0, gamma of 1. A variation of gamma is a family of curves that is going to interpolate gamma, as follows. So we can see it as a map depending on two parameters, S and T. So we still denote, in general, gamma, the variation of the curve. This is just that we are going to use two parameters, S and T. So S usually is defined on a small interval around 0, negative epsilon plus epsilon, and T is defined on 0, 1. Okay, and we say that this variation of gamma interpolates gamma in the sense that gamma of 0t is equal simply to gamma t. So you should have in mind, when we speak of a variation of a curve, you should have in mind something like, I have a curve gamma, on the manifold, and I will consider a tube of curves around gamma. So the first one will be gamma of 0t, and then you have another curve, gamma of st. Okay, so it should be seen as a tube around gamma. That is, we want somehow to move smoothly the curve gamma around in the manifold. So there is a specific case of a variation which is of interest for us a little later. This is when the starting point of the curves are always the same. So you could imagine that you have variations, where the start point is fixed. So in that case, this is not really like a tube that you should have in mind. This is more like a fan of curves. Okay, so the two pictures will be okay for you to have in mind when we speak of a variation. Okay, so if we have a variation of a curve, there is an important object which is associated to it, is a so-called variation field. So if gamma of st is a variation of a curve gamma, we have two types of field, the velocity field and the variation field. So the first one is, for instance, the velocity field. It's simply given by the derivative of gamma with respect to t. So this is dt of gamma of st. Okay, so these are the tangent to the curves. So the velocity field is simply tangent to each of the curves. Okay? So if you have gamma of st, the velocity field is here. And the second field, which is important, associated to the variation, is the so-called variation field. This is a field which is transverse to the velocity field. And this field describes how does the curve gamma move around in the manifold. So this is defined as a derivative with respect to S. So I will call it Y, you know, and this is the notation I'll be using today in class. You'll understand later that this Y is going to be a Jacobi field when we are going to do geodesic variations. So the variation field of the variation gamma of st is defined as a derivative with respect to S now. Okay, so this means how do we move the curves around? So you should imagine that you have something like this. So if you have your tube or fan of curves, the variation field is going to be transverse, right? And it describes how we move the curve infinitesimally in the direction of S. Does it make sense to you? So these two fields are only defined on the set of all possible gammas st. So there is a basic commutation principle for variation, this is called the commutation principle, is that these two fields, they commute. That is, the velocity field and the variation field commute. So as a slight abuse of notation for the velocity field, I'm going to use the notation gamma prime. Okay, meaning that this is really the tangent to gamma. So the velocity field, we are going to denote it by gamma prime. It's a slight abuse of notation, okay, because strictly speaking, gamma depends on two parameters, okay, so gamma prime, you have to understand it as a derivative with respect to time. So the commutation principle is that the Lie bracket between y and gamma prime is always equal to 0. This is true for any variation of curves. Why is that? This is simply because the cross derivatives, ds and dt, they do commute. Okay, s and t are parameters taking value in a one-dimensional space. The two cross derivatives with respect to t and with respect to s commute. Okay, so this is very simple equality of the cross derivatives that comes from the Schwarz theorem. We write it geometrically in terms of the vector fields, the variation field and the velocity fields, as a commutation y and gamma prime. Because ds dt of gamma is equal to dt ds of gamma. Okay? So this is very basic, this Lie bracket properties, that is commutation principle, but you'll see that it plays a fundamental role in the computation for the Jacobi equation that we are going to do in a few minutes. Is it clear for you at this point? Okay, very good. So now let me speak about the kind of variation which is interesting for us, which is going to be the geodesic variations. This is a specific case of variation of a given curve. This is a variation by geodesic. That is, any of the curves, in my tube is going to be a geodesic. So we work with a connection. Remember that by geodesic, I mean a geodesic with respect to a given connection on the manifold. So nabla will be a connection on M. Remember that at this point, I did not yet speak of Riemannian or pseudo-Riemannian structure. So really, when I speak of a geodesic, it has nothing to do with something which is length minimizing. Okay, so get this out of your mind. At this point, a geodesic is only related to a connection. That is, this is a solution of a second-order nonlinear differential equation associated to the connection. So recall that a geodesic gamma is a solution of the second-order ODE on the manifold nabla gamma prime of gamma prime is equal to 0. Okay? It was our definition of a geodesic. So in that case, we have what we call the notion of geodesic variation. This is going to be a tube or a fan around gamma, so that any of the curve is going to be a geodesic itself. So the geodesic variation of gamma is a variation gamma st. So again, S will be defined, on a small interval, negative epsilon epsilon. And this is a small variation such that for all S in its interval of definition, the curve gamma S dot, is a geodesic itself. Does it make sense to you? Okay. So our question, for the next 5 minutes will be to understand what could be the variation fields of a geodesic variation. And we are going to see this is what we call a Jacobi field of the connection nabla. So we now study the variation field of a geodesic, of a given geodesic, okay, so the notation are as before. You have your geodesic variation of gamma. Okay, and we have the variation field. We describe how we translate gamma to gamma st. This is what it does, the variation field. Okay, this is infinitesimal translation from gamma to gamma st. Now, let y be the variation field of this variation. That is, as before, y is the derivative with respect to s of gamma st. And I will try to get an equation on y based on the fact that any of the curve is a geodesic itself. This is something that should be doable, right? Because any gamma, when you fix the parameter s, is going to solve a second-order differential equations. So our question is, how can I perturb solution of second order differential equation so that I get the solution of the same equation for a different time, for a different parameter s. Okay? So we are going to see that y solves a linear second order differential equation, which is called the Jacobi equation. So this Jacobi equation is actually pretty simple to obtain. So we obtain it as follows. The idea is to infer, that intuitively y should satisfy a second order equation. It comes from the fact that gamma itself, satisfies the second order equation. So we write the equation for y, which is seen as a vector field along the curve gamma. This is what y is, right? You have a vector field which is defined along gamma. And I'm going to write the following computation along the curve gamma. That is, all these computations are going to be performed at s is equal to 0 at the end of the computation. Okay, which is the object I'm trying to perturb. So the y is seen as a vector field along gamma. As a consequence, of what we did last week, I am able to differentiate y along gamma. This is what we call the covariant derivative of a vector field along a curve. So I'm going to compute two covariant derivatives of y along gamma. And I'm going to do my computation like this. So first, I will, and this is a simplification I will make, for the rest of the class, is that I will assume that the torsion of the connection nabla is equal to 0. Just, to simplify a little the Jacobi equation I'm going to obtain. But, and this is done in the book, my computation can be extended very easily to the case where the connection nabla has a torsion. So we have, assuming that nabla is torsion-free, and this is an assumption I'm going to make up to the end of the class today. So nabla gamma prime of nabla gamma prime of y will be computed as I can switch the role of gamma prime and y using the torsion tensor. So first I will write it as nabla y of gamma prime, okay, using the fact that the torsion is equal to 0, I will have the Lie bracket between gamma prime and y, right? Because the torsion is equal to 0. So I just write the derivative of y with respect to gamma prime as being the derivative of gamma prime with respect to y minus the Lie bracket. But what is the Lie bracket? I told you that we have the commutation principle between the variation field and the velocity field. So the Lie bracket is equal to 0. So I get nabla gamma prime of nabla y of gamma prime. This is the first way to simplify the second derivative of y with respect to gamma prime. And now I'm going to write this second derivative in terms of the covariant, or in terms of the curvature tensor. So now remember, and this is a definition of the curvature tensor, that we have the following equality. So we now recall that the curvature tensor R of the connection is given by the following formula. R of gamma prime. So I will apply the curvature tensor to gamma prime, y, and gamma prime. Okay, so in that case, by the definition simply of the curvature tensor, this is equal to nabla gamma prime y of gamma prime minus the Lie bracket of nabla gamma prime nabla y, okay, of gamma prime. So in this expression of the curvature tensor, a lot of stuff are going to cancel because the first one is 0 from the commutation principle. Okay, so I'm just left with a Lie bracket between nabla of gamma prime and nabla of y. So I will write it explicitly. So I get as a first term nabla gamma prime nabla y of gamma prime. And the second term is plus nabla y of nabla gamma prime nabla gamma prime. But what is nabla gamma prime of gamma prime? Can someone tell me to make sure that you are following? That is the second term, you know, in the curvature tensor is going to be equal to what?
0.
0, very good, because I have a geodesic. This is a geodesic equation. So I end up here with the property that R gamma prime of Y gamma prime is simply equal to nabla gamma prime nabla Y of gamma prime, which is exactly the term that I computed before here. Okay, so I put them in red and they are the same term. So I deduce that we have the following equation. Y is going to satisfy the second order equation along gamma. Nabla gamma prime of Y plus R of gamma prime Y gamma prime is equal to 0. This is called the Jacobi equation. Okay, so this equation is called the Jacobi equation, related to the connection nabla. Okay, so terminology, any solution of the equation along gamma is going to be called the Jacobi field. Okay, that is, any solution of this equation is called a Jacobi field. So this is the Jacobi equation for connections without torsion. The computations, you know, when nabla has a torsion is not much more difficult, but the Jacobi equation is going to involve several other terms, you know, that make the study of the Jacobi equation a little bit more difficult. I let it to you as an exercise to write the Jacobi equation in the case where the connection nabla has a torsion. Okay, so if we summarize a little bit the computation I show you, it shows that if you have a geodesic variation, the variation field of this variation is going to be a Jacobi field. This is what we proved. Okay, so if gamma of st is a geodesic variation, this is what we proved, then the variation field is a Jacobi field. So this is not difficult. You see, my computations were not very involved. I just commute some covariant derivative, and I get almost straight away, you know, the Jacobi equation. So don't be scared, you know, by the Jacobi equation. It's actually a simple object. Okay, that is, Jacobi fields are not something which is very fancy, and they are extremely useful to do concrete computations on manifold. You know, they provide really an exact way of describing geodesic variations. And they are explicitly computable on a lot of manifolds. So this is the basic principle you should take, away from the beginning of the class today, is that if you have a geodesic variation, the variation field is a Jacobi field. So now let me speak a little bit about the Jacobi equation itself. How do we solve it? How do we understand it? Okay, and how do we know that we can always solve the Jacobi equation? Okay? So study of the Jacobi equation. So if we summarize just a little bit, if gamma is a curve, so I don't even need to speak anymore of variation, because if I consider a curve, I can simply define the Jacobi equation along this curve. Okay? And the solution of the Jacobi equation is going to be a vector field defined along this curve. So to define the notion of Jacobi field and Jacobi equation, actually, I don't need a variation. So if gamma is a curve, we have just seen that the Jacobi equation along gamma is as follows. So this is the second derivative of y plus r of gamma prime y gamma prime is equal to 0. Okay? So to study this equation and to see that this is a second order linear equation, this is convenient to work with parallel frames along gamma. So it seems that the screen is frozen on WebEx. There is a little lag, so I'll wait for 5 seconds. It's like magic. I don't do anything, but it writes by itself. Okay, here we go. So it seems that we are live now. So this is the Jacobi equation along the curve gamma. So I was telling you that if you want to solve explicitly this equation, this is convenient to work in what we call a parallel frame along gamma. So this is this frame that we are going to introduce now. So let x, to fix the notation, to be gamma of 0, be the starting point of gamma. Okay? So consider x. So it's a little annoying. There is a lag between what I'm writing and what I am saying. And now it seems to be frozen. So now it seems that this is completely frozen. Okay, so we are live, but I hope that it's going to get fixed during the lecture, otherwise it's a little annoying. Okay, so x is the origin of gamma. I'm going to consider a frame at the point x. That is, let x naught up to x n minus 1 be a frame that is a basis of vector field at x. Okay, so this is only a basis at the point x. For convenience of the computations, and we can always do that, I'm going to choose the first vector in the basis, x naught, to be equal to gamma prime. That is, the first vector in my basis is going to be given by the velocity of gamma at x. You should imagine that the situation is like this. I have a curve gamma. Okay. And if this is, for instance, in 3D, x naught is going to be a tangent to gamma prime, and you have x1. So we can obtain a frame along gamma, which is called a parallel frame, by using parallel transport along the curve gamma. So this frame at x can be parallelly transported along the curve gamma. Okay, using the parallel transport that we studied last week. Okay, so this is common to still use the same notation, that is x0 up to xn minus 1. Okay, and n here is the dimension of the manifold. So we consider the parallel transport from 0 to t along gamma of xi. Okay, so these fields, vector fields, now which are defined always on all points of the curve gamma. So a basic question to make sure that you are following, if I transport parallelly x naught along gamma, what do I get? Remember that x naught at the point x is given by gamma prime of 0. So if I transport parallelly gamma prime of 0 along gamma, what do I get? Keep in mind that gamma is a geodesic. So if I transport parallelly gamma prime along gamma, what is the vector field I get? Can someone tell me? Has someone an idea about this one?
The velocity?
Very good, exactly. Because the velocity is parallel along gamma. This is a definition of a geodesic. Okay, you can take it as a definition of a geodesic, is that the velocity field is parallel along gamma. So x naught is always equal to gamma prime. Okay. So it seems that WebEx is still lagging. It's a little, it's a little annoying because you would have thought, that by the middle of the semester almost, they will be able to handle a lot of traffic, but not. So the connection is still very slow. So as Marco was saying, gamma prime is x naught. That is, gamma prime is parallel along gamma. So the other vector fields, x1 up to xn, n minus 1, well, you should see them as being parallel fields along gamma. So x naught up to xn minus 1 is what we call a parallel field along gamma, a parallel frame. So parallel frames are used to solve the Jacobi equation. So now I will write, the Jacobi equation in this frame. Because any vectors, along gamma can be expressed as a linear combination, of these xi. So the idea to solve the Jacobi equation and really to understand it is we are going to write, the equation in this frame. That is, we look now for a solution of the Jacobi equation in this frame. That is, yt is a vector field along gamma. So we know that it can be expressed in terms of the vector field xi using some coefficients yi. Okay. So the screen is still frozen. Here we go. So we look for a solution of the Jacobi equation as a linear combination of elements in this parallel frame. Okay? So now let's write the equation we get on the component yi. So if we plug in this expression inside of the Jacobi equation, we are going to get equations for yi, right? So we get so I will write all the steps. And introduce what we call the curvature tensor along the curve. So the first term is nabla gamma prime of the sum of the yi and xi. Okay? The second term is r of gamma prime, sum of the yi and xi and gamma prime. So now let's compute the first term. I will compute step by step. So first I will compute the first order derivative. So if I differentiate sum of the yi xi with respect to gamma prime, what do I get? It's important at that point that you understand how to differentiate vector fields along curves. So what will be the derivative with respect to gamma prime of the sum of yi and xi? Has someone an idea? Keep in mind that xi is parallel along gamma. Okay, this is a definition of xi. So what will be the first term? Someone would like to give a suggestion about the first term? How do we compute it? So nabla gamma prime of xi is 0. Okay. So the derivative with respect to gamma prime is only to hit yi. And then when I differentiate a function along the curve, this is the usual derivative. So this is yi prime. So I apply this once, and then the second time, I will get the second derivative of yi. So the first term is the sum of second derivative of yi with respect to t. Okay? And you have xi. The second term, I use the tensorial property of the curvature tensor, so this is linear with respect to the second component, and I get the sum of the yi r gamma prime xi gamma prime. Are you with me? Okay, good. So now I will introduce the curvature tensor along the curve gamma. So we now introduce so sometimes this is denoted simply by r of gamma prime. This is an endomorphism which is defined along the curve as follows. It is defined by if you have a vector field along gamma, r gamma of x is equal to r gamma prime x gamma prime. Okay? So this defines an endomorphism along gamma. Are you with me? Okay, good. So then I can rewrite, the Jacobi equation using this curvature endomorphism and the component of the curvature endomorphism inside of the frame xi. So this is still completely frozen. So it seems now the connection is completely lost. Can you still hear me? So I think I need to reconnect. Okay, so I will leave the meeting for 5 seconds and I will try to reconnect. Can you hear me? Hello, Genhi.
I,
So it seems that you're the first one. It's a little annoying, you know, that Yukon is not able to fix the problem with WebEx. That's incredible.
yeah, I think that the traffic is so heavy at this point.
Yes, but I mean, they should pay for that because the students pay a lot of money, you know, to
Yeah,
have online
absolutely.
courses, and if it does not work, that's really a problem.
Yeah, indeed, yes.
So let's see if other people are coming. Are you still connected to the WebEx session?
I already quit from the WebEx.
Ah, okay. Because I wonder if the other people got the link.